Okay, let's continue the discussion. Today we start section 7.7, graphs of the tangent, cotangent, cosecant, and secant functions. Okay, so first we start from the graph of the tangent functions. From the previous study, we know that the tangent function is a so-called periodic functions. The fundamental period of the tangent is pi. Okay, so we know that the tangent of x plus pi is equal to tangent of x. So it means if we know how to graph the tangent function over an interval with a length pi, we just repeat it, we can get the graph of a whole tangent. Okay, so we only need to graph the tangent function over an interval of length pi, because after that we just repeat this this graph, we'll get the whole graph. And we also know that the tangent function is sine of x over cosine of x. Tangent is sine over cosine, and plus cosine of pi over 2, cosine of negative pi over 2 are both 0. So it means tangent of x is undefined at negative pi and positive pi over 2. Negative pi over 2 and positive pi over 2. So for these two reasons, we now study tangent of x over the interval with the length pi. We want it symmetric about 0. So it's from negative pi over 2 to positive pi over 2. But they cannot include the to endpoint, so it's an open interval. So we only study the behavior of tangent function over negative pi over 2 and positive pi over 2, open interval. Okay, this interval has length pi, and this interval does not include two endpoints because of cosine is 0. Okay. Okay, so the graph of the function is a trace of the values for the corresponding x. So now let's give you have the list of the tangent function for some special values. So because the interval is between negative pi over 2 and positive pi over 2, let's assume this angle is 0, angle is pi over 6, pi over 4, pi over 3, not pi over 2. Pi over 2 is not in the domain. And then negative pi over 6, negative pi over 4, negative pi over 3. So they are the angles. And then we put the x value and the y value. Okay, and the corresponding point on the graph. Let's make it complete. Okay, so we know that tangent is 0, 0. Tangent pi over 6, tangent 30 degrees is square root of 3 over 3. Tangent pi over 4 is 1. Tangent pi over 3 is square root of 3. Okay, and we also know that the tangent function is an odd function. What is an odd function? tangent of negative x is equal to negative tangent of x. This is what we mean. Tangent is an odd function. So when you have this odd function, tangent of negative pi over 6 is negative. So here, let's just do one example. Tangent of negative pi over 6 is negative tangent of pi over 6. Okay, so negative tangent pi over 6 is a negative square root of 3 over 3. So you get a negative square root of 3 over 3 and negative 1 negative square root of 3. You just get the same opposite value but with the negative sign. It's because a tangent is an odd function. Okay, so you have x. Tangent, the value give you the y value. Okay, so you put them together, you see this point, the point on the graph is negative pi over 3, negative square root of 3. Here is a negative pi over 4, negative 1. Here is a negative pi over 6, negative square root of 3 over 3. Here this is a 0, 0. This one is a pi over 6, root 3 over 3. This is a pi over 4, 1. And this is a pi over 3, root 3. So they are not intervals. They are the xy coordinates of the corresponding point on the graph of tangent function. Okay, they are not intervals. Okay, so we are going to label them or plot them on the xy plane and check the graph. Okay, so we only label these limited point because it's not easy to really get the exact value of tangent function or trigonometric function. Okay, so this is pi over 2. Symmetrically, this is a negative pi over 2, pi over 4, negative pi over 4, pi over 6. Pi over 6 is about here, pi over 3 is about here. So pi over 6, pi over 3. Here's negative pi over 6, negative pi over 3, negative pi over 6, negative pi over 3. Okay, so and 0, 0, 0, 0. Okay, this is 1 point. And pi over 4, 1. When you have pi over 4, you have 1. 1 is here, possibly here. And pi over 6, square root of 3 over 3. You can use calculator to get the approximation of root 3 over 3. Root 3 over 3 is almost what? It's almost 0.58. So it's like half. Okay. And the root 3 with a calculator, it's about 1.73. 1.73, like this. They are not on a straight line. It's a curve. So just connect them smoothly. And the other part, they are symmetric because of the other function. You just rotate it pi radian or rotate this graph 180 degrees. So you get the other part. The other part is it's a negative 1. Negative 1.73. Okay. So far, at least we can get the idea of those graphs. Okay, so that's the demonstration of the graph in this limited period, limited interval. And now we want to see what will happen if the point is very close to pi over 2 or close to negative pi over 2. So when x is close to pi over 2, remember the tangent is sine over cosine. So we're going to study the numerator under the denominator. Sine x will be close to 1. Sine pi over 2 is 1. And at the same moment, cosine of x, cosine pi over 2 is 0, is close to 0. So you divide 1 by an extremely tiny number. Then this tangent x is close to infinity. When we say it is close to infinity, it means tangent of x is positive and becomes large unlimitedly. As x is close to pi over 2. So when you have this idea in mind, and you can get so from the evaluation, we can only sketch this part. And because of this argument, when x approaches pi over 2, this graph will be as high as possible. And it's an odd function. When x approaches negative pi over 2, it will be as negatively large as possible. Okay, when x is very, very close to pi over 2 or negative pi over 2. So this is the graph of tangent function over the interval negative pi over 2 and positive pi over 2. And this graph tells us these two lines, x equal to negative pi over 2 and positive pi over 2, are the vertical asymptote. Asymptote. Vertical asymptote. Okay, so this is the graph over this interval. And remember, this cotangent function is a periodic function with a period pi. This is pi. So if you want to get other part, let's just extend it to the left. Remember, the period is a pi, so you subtract negative pi over 2 by pi, you get a negative 3 pi over 2. So the graph, you just copy it. It's like this. You see? So it's like you shift it to the left, and you can shift it also to the right, one by one. So you will get a lot of such curve. Okay, and also from this shift, you can see that negative pi over 2 is a vertical asymptote. Pi over 2 is a vertical asymptote. Negative 3 pi over 2 is also a vertical asymptote. If you move to the right, you will see that 3 pi over 2 is also a vertical asymptote. How do I get 3 pi over 2? How do I get this vertical line? You see, from negative pi over 2, you subtract pi, you get 3 pi over 2. This is negative pi over 2 minus pi. To the right, you are going to do addition, so you get pi over 2 plus pi. So that gives you 3 pi over 2. Okay? You move to the right, you add pi. You move to the left, you subtract pi. Okay? So, and then you can observe it. You have a negative 1 pi over 2, 1 pi over 2, 3 pi over 2, negative 3 pi over 2. You continue to the left, you will have negative 5 pi over 2, negative 7 pi over 2. You move to the right, you have pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. The pattern is that the numerator is always the odd multiple of pi. 3 pi, 5 pi, 7 pi, 9 pi, 11 pi. Denominator, of course, is always 2. Okay, so that is the pattern. So let's summarize the property of the tangent functions. Okay, what is the property? This is on page 578. The properties of tangent function. Okay. first. You see here, we always skip those points. So it just means the domain does not contain those points. So the domain is the set of all real numbers except, the important thing is this except part, except odd multiples of pi over 2. Odd multiple, one time pi over 2, 3 times of pi over 2, -1 times pi over 2, -3 times pi over 2. So only odd multiples of pi over 2. And here this odd means it can be positive odd or negative odd. Okay, it can be positive or negative. Okay, second, this is domain. You will skip some point. The range is the set of all real numbers. Okay, so the range does not miss any value. You can see here, it covers from top to the bottom all the points, all the possible values. So the range is from -infinity to +infinity. So sometimes you can say that the range is from -infinity to +infinity. It's another way to say the set of all real numbers. And 3, the tangent function is an odd function. We summarize the property, so this is something we already know. So here we explain what is odd function as the symmetry of the graph with respect to the origin indicates. So there are 2 ways to understand this odd property. Okay, so what is odd? Odd has 2 explanations. First, you have the right branch, you rotate it 180 degrees or pi radian, you can get the left branch. This is one explanation. You have the right part, you rotate it pi radian, you get the left part. Or what is odd? Odd means whenever you have a point here, you have a point on the graph, you connect it to the point with the origin and you extend it, and you will intersect the graph at another point. The property is that this distance is equal to this distance. These 2 distances are equal. Okay, so you start from the point, you connect it to the origin, and you extend it to the left part, intersect the graph at the second point, and the distance from the original point to the origin is equal to the distance from the origin to the second point. They have the same distance. This is another explanation of odd symmetry. Okay, you can either use rotation or you use the segment and the extension. Okay, so that's a third property. The tangent function is an odd function. The fourth property, the tangent function is periodic. With period pi. So here when we say with period pi, we actually mean with the fundamental period pi. So tangent x plus pi is tangent of x. From this, of course you can say that tangent of x plus k pi, whatever integer multiple of pi, it is also equal to tangent of x. For whatever integer, positive or negative. So k pi is also the period. Here we always mention with the period pi, this pi is the fundamental period, the smallest positive period. Smallest positive period. Okay? That's the property for the tangent function is a periodic function. And remember that sine and cosine are both periodic, but with period 2 pi. Okay? And the property 5, the x-intercept. The x-intercepts are, let's check the graph. The x-intercepts. So from this graph, we can see this is 0. And here, this is negative pi. You shift it to the left by the period pi, you get a negative pi. Shift to the left, a minus. You can expect it. If you shift this 0 to the right, it is pi. So the intersection of the graph with the x-axis is always 0, pi, 2 pi, 3 pi, 4 pi, or 0, negative pi, negative 2 pi, negative 3 pi, negative 4 pi. So the x-intercepts are ... and negative 2 pi, negative pi, 0, and pi, 2 pi, and ... So it is all k pi with integer k. So k can be positive integer and negative integer, or 0. So this is x-intercept, the intersection of graph with the x-axis. The y-intercept is 0. So first of all, whenever you have a function, there is at most one y-intercept. So sometimes the function has no y-intercept if the 0 is not in the domain. And if 0 is in the domain, the y-intercept is always the f of 0. So here, f of 0 is a tangent of 0. Tangent 0, we know that tangent 0 is 0. So the y-intercept is just 0. There's only one. Okay, so this is a intercept. You can have infinitely many x-intercept like this tangent of x. It has infinitely many x-intercept. But it can have at most one y-intercept because you have a function. Okay, 6. The vertical asymptotes occur at x equal to ... and negative 3 pi over 2, negative pi over 2, pi over 2, pi over 2, and 3 pi over 2, and ... And you can say that all k pi over 2 with odd integer k. So k pi over 2, but k can only be odd integer. Or you can say that all k pi plus pi over 2 with integer k. If you put k on the numerator, the k pi over 2k is an odd integer. If you put k pi plus pi over 2, then k can be anything. You see here. How do you get pi over 2? It's 0 pi plus pi over 2. How do you get a negative pi over 2? It's a negative pi plus pi over 2. Negative pi plus pi over 2 is equal to negative pi over 2. So it's always the multiple of pi and plus pi over 2 is shifted to the right. Okay, so either way, you can just write it like this, or k pi over 2 with odd integers, or k pi plus pi over 2 with whatever integer k. Just choose one representation and memorize it. Okay, so that's all 6 properties, basic properties of tangent functions. All 6 basic properties of a tangent function. They are on page 578, so you can check it on the book. Okay, now let's modify or change the tangent function a little bit in order to get a general graph. Okay, so example. So graph y equal to 2 tangent of x minus 1. Y equal to 2 tangent x minus 1. Okay, so how do we graph it? So first, you graph the regular tangent function. So tangent function, we normally just graph 1 and repeat it. So tangent function is like this, between negative power 2 and the positive power 2. Okay? And then this number 2, you see here, when you have a x equal to power 4, tangent power is 1, but times 2, you stretch it. Times 2, it becomes 2. So you see here, tangent pi over 4 is equal to 1, but 2 times tangent pi over 4 give you 2. So this coefficient 2 will stretch the graph of tangent function along the vertical direction. Okay, so how do we get the 2 tangent of x? So you still get the negative power 2 part and the positive power 2 part. Regularly, it's for pi over 4 is a 1, but now for pi over 4, it's from 1 you get 2, so it's more steep. Okay, just stretch it along the y direction. Okay, so it's why we do this stretch process is because of this observation. Okay, so this is here is a tangent of x. This is a 2 tangent of x. Minus 1. We still need minus 1. Minus 1 means you're going to shift this whole graph downward 1 unit. Okay, so you're going to shift everything down. So here's 1. So 0 is moved to negative 1. So it's like this. So this is a 2 tangent of x minus 1. So shift everything down. So when you get this part, when you get this graph, you're going to repeat it to the left and to the right to get the complete graph. Okay? And you see here, you only stretch it or shift it vertically. You do not change the x part. So the domain is still the domain of the original tangent of x. Is everything but k power 2, k odd. Okay, so that's the graph of the function. How do we sketch it? We always start from the standard graph, the graph of the standard function, tangent of x, and then we're going to modify it step by step. We always just modify every time just one step. We don't do two operations at the same time, just one step. Okay. Okay, this is the first example. Let's see the second one. So here in the first example, we only either stretch or shift the graph vertically. Now let's see how do we do it horizontally. Okay, so we are going to graph y equal to 3 tangent 2x. So we have the coefficient for x. Okay. So how do we do that? First, same thing, you sketch the graph of tangent of x. Okay. Okay, now let's see. Tangent of x is undefined at pivot 2. So when x is pivot 2, tangent x is undefined. And now you have 2x. It means when 2x is pivot 2, tangent x is undefined. You see, when 2x is pivot 2, tangent pivot 2 is undefined. So from this, you get x is pivot 4. So this number 2 actually does not change the graph a lot, but it shrinks the domain of the function over this one period. So you can more or less get the same graph, but you have to change the label. Sorry, this is 4. Originally it's from negative power 4 to positive power 4, but now you have to change it from negative power. This is negative power 2 to positive power 2, and now you're going to change it to negative power 4 to positive power 4. How do I get power 4? I let 2x be power 2. You solve for x, you get x equal to power 4. Okay, and the graph has the same shape. Just compress it. So this is the way to find the left and the right bounds for this one period. And then number 3. Number 3, it plays the same role as the previous example. You're going to stretch it along the y direction. So you got power 4, negative power 4. You're going to make a more steep graph like this. Okay, so this is a 3 tangent 2x. 3 tangent 2x. Of course, you can have certain label. Here you get a power 4, you get a 1. This part you will get a power 8. Why do I get power 8? 2x is power 4. Then x is power 8. So when you get power 8, you get a 1. This is 1. Assume this is number 1. And now multiply by 3, so power 8. You unfortunately have to label it by 3, even though maybe they are not scaled in the same scale, but it doesn't matter. Just label them by 3. Okay, so that's the graph. And normally we only use pi over 4 to demonstrate the scale, because if we use other angles like pi over 6, pi over 3, you will handle square root of 3 or square root of 3 over 3. Those numbers are not so simple. So you have to use calculator to understand the number. So we don't choose that. We only choose pi over 4. We only choose pi over 4 from the original graph, because pi over 4, tangent of pi over 4 is 1, so it's more clear. Okay? Okay, so that's the tangent, 3 times tangent of 2x, the graph of it. And of course, from here you can see that the originally 2x cannot be, you see here, 2x cannot be k pi over 2. K is an odd integer, right? That's the point, not in the domain. And from this, you get k pi. You solve for x, you get k pi over 4. You don't change any property about k, so k is still the k represents the odd integers. So the domain is equal to x is not equal to k pi over 4. K is an odd integer. Okay, so this is the domain. And the range is still from negative infinity to positive infinity. Okay, so here we only put 2 here. Of course, you can put plus or minus 1, 2, 3, whatever. If you put plus or minus at the tail, you're going to shift the graph of tangent vertically. Just shift it. You do not stretch anything. Here, we actually compress the graph of tangent along the x direction and stretch it along the y direction. So we have 2 steps. Okay. So this is the discussion of a graph of tangent function. We have the list of 6 basic properties for the tangent function, and we know that basically that the graph tangent function is from left to right. It's increasing. It's a odd function, and it has a lot of vertical asymptotes, and the domain is not defined over whole number lines. It skips some point. Okay, and it has infinitely many intercepts. Okay, so that's the tangent. And with this experience for the tangent function, we can get the graph of cotangent function quickly. Okay, so what is the graph of cotangent function? We first get the idea. Cotangent is cosine over sine, and sine is sine 0 is 0, sine pi is 0. So first, this is what we know. And from here, we know that the cosine is undefined at 0 and pi. Cotangent is undefined at 0 and pi. And also, cotangent function is a periodic function with a period, fundamental period, pi. So we only need, like the tangent function, we only need to graph the cotangent function over the interval with the length pi. And now cotangent function is not defined at 0, not defined at pi, so we only study y equal to cotangent of x on 0 and pi. So it's between 0 and pi. Those 2 points give us the bounds of the domain. So we are going to have this, and in this part, we will have the following table. It's not like the tangent function. Tangent function have symmetric part. Here it's not symmetric. So we have, it's not defined, it's undefined. So we have 2 circles here, 2 circles here. So the table is the following: pi over 6, pi over 4, pi over 3, pi over 2, and 2 pi over 3, 3 pi over 4, and 5 pi over 6. So how do we get it? 6, 4, 3, 2. And then you have 2, 3, 3, 4, 5, 6. Okay? Okay, so you get the cotangent of x. Cotangent pi over 6 is root 3. Cotangent of pi over 4 is 1. Cotangent pi over 3 is root 3 over 3. Cotangent of pi over 2 is 0. And the other part, you see here, you are going to copy this and put a negative sign. So it's a symmetric. It's symmetric about 0, but here is positive, here is negative. And you have x point, y value, and you put them together, you will get the coordinate of the point on the graph. Okay, so the graph is the following. One x is pi over 6, y is root 3. One x is pi over 4, y is 1. One x is pi over 3, y is root 3 over 3. One x is pi over 2, y is 0. And here we just copy 2 pi 3, negative root 3 over 3, and 3 pi over 4, negative 1, and 5 pi over 6, negative root 3. So this is just the table. This table is on page 579, table 11. So if you don't copy it, you can just check this table on the textbook. So, okay, so after you get this table, you are going to label them. Cotangent of pi over 2 is 0, so this is the best. And the cotangent, this part is positive, this part is negative. So here, let's say this is pi over 4, this is pi over 2, it's pi over 4. And here you have 3 pi over 4. And then this is a pi over 3. This is pi over 6. Here you get 2 pi over 3, 5 pi over 6. Okay, and then you're going to label them. This you get a 1 here. You get this number, so you label them, and you get the symmetric part, but it's negative. Something like this. Based on this evaluation table, you can only sketch this this piece, and then we're going to go through the similar study. So when x is close to 0, when x is close to 0, cosine of x is close. Cosine 0 is 1, is close to 1. Sine x is close to 0. So 1 over 1 over 0, cotangent 1 over 0. So the cotangent of x is positive and large. You divide a number, a non-zero number, by almost a zero number, so you will make the value very, very large. So if we have such discussion in mind, like the tangent, we'll have the similar discussion, we can get the graph of cotangent. The graph of cotangent, remember we only studied the domain over 0 and pi, excluding 0 and pi. So the graph of a cotangent looks like this. And it is periodic, so it's negative pi. You're going to shift it here. Okay, so every place you're going to repeat this. So this is the graph of the cotangent function. Okay, so graph a cotangent function like the tangent function. You can also make your own list of the properties for the cotangent. Let's make it. We almost copy that list, but we have some modification. So properties of the cotangent function. First is about the domain. The domain is the set of all real numbers except, so the important part is the except part, except k pi. So this one is simple. 0 is not included, pi is not included, negative pi is not included, 2 pi, negative 2 pi, 3 pi, negative 3 pi. K is an integer, no even odd. Okay, so cotangent function is undefined at all k pi, undefined at all k pi. Okay, so that's our domain. The range is the set of all real numbers, period. So no exception. So range you see here is from negative infinity, from bottom to top. It covers all possible values. So this is the range. And number 3, the cotangent function is an odd function. So you can see that you have this piece, you rotate the pi radian, you get exactly this. Or you get a point, you connect it to the origin and extend it to the next point. This distance is equal to this distance. So it's the same the second explanation of an odd function. So it's an odd function. And for the cotangent function is periodic with period pi. So cotangent is also the periodic function with this time with a period pi. The same thing. Okay, and 5. The x-intercept. The x-intercepts. Okay, let's see what are the x-intercept. Pi over 2, negative pi over 2, 3 pi over 2, 5 pi over 2. You see, they are exactly the missing point of the domain of a tangent. So they are negative 3 pi over 2, dot dot dot, and negative pi over 2, pi over 2, 3 pi over 2. You can say that all k pi over 2, k is an odd integer, or all k pi plus pi over 2, k pi plus pi over 2, k is an integer. Either way, just pick up one explanation or one representation, that's enough. So the x-intercept and y-intercept, there's no y-intercept because 0 is not in the domain. There is no, let me put this capital letter. There's no y-intercept because 0 is not in the domain. Okay, so no y-intercept. And 6, asymptote. So the vertical asymptote x equal to k pi. K is an integer. X equal to k pi. All the, see here, all the 0 pi, negative 2 pi, 2 pi, negative 2 pi stuffs. So whenever the point is not in the domain, they provide the vertical asymptote. Okay, so that's the corresponding list for the cotangent. So you have the tangent. There, the list is on the textbook, and then you can get this as corresponding list for the cotangent. This list is not on the book. You can make it by yourself. Okay, so tangent and cotangent, they are very, very close to each other. Okay, so you just get the similar idea. Okay, so you can shift or stretch or compress the graph tangent. You get another graph of tangent. You can all do the similar technical steps to get the graph of other cotangent. Okay. Okay. And next, let's check the graph of a secant and a cosecant. Secant of x. Secant of x, by definition, is 1 over cosine. So let's see what is a secant of x. I'm sorry. First, we get the graph of a cosine. Graph of cosine is like this. Okay. Reciprocal. A 0 has no reciprocal. Okay, so 0 will those points will be undefined. And when you flip 1, you get a 1. When you flip 1/2, you get a 2. So when you repeat that process, you will see that this branch, let me use other color. will be the reciprocal graph. And here, and here, here's the similar. Here's similar. Okay, so the red curves are the curves of secant of x. The red curves are the graphs of the secant of x. And the secant of x also has domain, the set of all real numbers except, you see here, except those points, except k pi over 2, k is an odd integer. So domain is everything except x is not k pi over 2, k is odd. The same domain for the tangent because they share the same denominator. Tangent is sine over cosine. Secant is 1 over cosine. They share the same denominator. They share the same domain. Okay, and also you see here, because you flip the cosine, this horizontal part between 1 and -1. The secant is either above the 1 or below the -1. So the range is y. Y is either greater than or equal to 1 or y is less than or equal to -1. So it's either above it, the 1 part or below the 1 part. Or you can write it, or you can consider that the opposite value of y is greater than or equal to 1. Okay, so that's another way to describe the domain and the range. Another way to describe the range of secant. Okay, so secant is 1 over cosine. And the cosecant, similarly, we can get the graph of a cosecant. Cosecant is 1 over sine. So let's okay, so again, whenever you flip the 0, you will get infinity. So those points are the undefined point. And then you're going to flip sine, you get a cosine. So the red part. Okay, so this is a graph of y equal to CSC, cosecant of x is 1 over sine. Cosecant of x, 1 over sine. And like the cotangent, cosecant, they share the same denominator, so they share the same domain. The domain is all real x except x is equal to k pi. K is an integer. The range is the same thing like the secant, because you flip the more or less the same curve, but with a different places. Okay, so this is a domain and the range. And another thing for this is that whenever you see dotted line in the secant and the cosecant, they give you the vertical asymptote. So the vertical asymptote are the x equal to k pi. Oh, sorry, not equal. Okay, so whenever the point is not in the domain, they give you the vertical asymptote. Here, the vertical asymptote. Let me write it here also. Vertical asymptote are the x equal to k pi over 2, k is odd. Okay, so this is a vertical asymptote for the secant. This is a vertical asymptote for the cosecant. Okay, so these two graphs for the red curves are on page 580. So you can consult these two pages on the graph on the textbook. Okay, so that's the explanation of the graphs of a tangent, cotangent, secant, and cosecant. And also we did two examples about stretch, compress the graph of tangent. We only did it for the tangent. Cotangent, we didn't do it. And now let's do one thing for the cosecant. Okay, just a similar thing. We just repeated the strategy we had. Okay, this is page 9. Okay, now we graph y equal to 2 cosecant of x minus 1. Okay, so first of all, this is cosecant of x, so you just sketch it. And remember, tangent and cotangent have period pi. Sine, cosine, secant and cosecant, they all have period 2 pi. So here we only sketch one period, and that's enough. So we first get cosecant of x. It looks like this. It has two branches. And then we get 2 cosecant of x. How do we get 2 cosecant of x? We just stretch it along the y direction. Okay? So here's a 1. Here's a negative 1. When you stretch it, 1 becomes 2, negative 1 becomes negative 2, 0 becomes 0. 0 is always fixed by this stretch, because 0 times whatever number is still 0. We don't say shift, we say stretch. Stretch. Okay, let's continue. Sorry. We stretch it along the y direction. So here, when you do it, you just change the label from 1 to 2. Negative 1 to negative 2. You get the similar graph. Because we don't have the exact scale, so we just change the label. And when you get this 2 cosecant of x minus 1, it means you're going to shift it. You shift the whole graph 1 unit down. Okay, so let's see. Here is 2. Then you shift it by 1, so 1 is here. Here is a negative 2. You shift it by 1, it's negative 3. Okay, originally the graph is from 2 to infinity. Now it becomes from 1 to infinity. Here it was from negative 2. Now it becomes from negative 3. So this is 2 cosecant of x minus 1. Okay, so that's the answer, the final answer. That's our final answer. Okay, so you need to do your exercise, the recommended exercise, and try to understand the whole steps. Okay, thank you.